Okay, today we're going to do one more lesson on inverses. We're doing inverse exponentials, and that will introduce the logarithm. So first we're going to do a little review of yesterday for the warm-up. We'll start by reading the problem. Determine whether the function is one-to-one, which means that the inverse is also a function. The function passes the horizontal line test. If it doesn't, we have to restrict the domain. Find the inverse of the function, the domain and range of the function and its inverse, then graph the function, the inverse, and the line of reflection. So there's several things within this one problem. Let's first decide whether it's one-to-one. Well, it looks like it's a quadratic by this 2 here, so I'm going to decide it's not one-to-one, so I need to restrict the domain. And we use the vertex to help us do that. So the vertex of this function is at the opposite of this number, so -2, the same as this number, so -1. We use that to tell us what the domain is. So for f of x, the domain is going to be all the x's have to be greater than -2, so x are greater than or equal to -2. And the range, this is a positive upward facing parabola, so all the y's are going to be greater than or equal to -1. And for the inverse function, we just switch these two numbers. These two numbers just get switched for the domain and range. So the domain of the inverse is x is greater than or equal to the range of the function, so -1, and the range is going to be y greater than or equal to the domain of the function, -2. So there's the domain and range of the function and its inverse. So we found we decided that it wasn't one-to-one. We found the domain and range of the function and its inverse. Let's find the inverse of the function now. So the inverse, we did that on the first day. You just make this a y and then switch x and y. So x equals y plus 2 to the second power minus 1. Now we solve for y. So we undo order of operations by adding the 1 to both sides. Remember, we're trying to isolate the y on this side. So the first thing is to get rid of this 1. So that's a 0, so we just have y plus 2 squared on this side. And we have x plus 1, because those are not like terms, on the left-hand side. Now we're going to undo the power. So undo the power by taking the square root of both sides. And you end up with square root of x plus 1 on the left. And the square root undoes the square, so you just have y plus 2 on the right. You don't need the parentheses anymore. To get the y alone, now I need to subtract that 2 that was inside the parentheses. And remember that 2 does not get subtracted from the 1 under the radical, because this is all under the radical. So you can't combine something that's not under the radical with something that is under the radical. So you keep it square root of x plus 1 with a minus 2 on the outside. And then just put your inverse notation in. Square root of x plus 1 minus 2. There's your inverse. And now all we have left to do is to graph this. So we have to know the vertex of the function, which was -2, -1, to help us graph it. So we know that the table for f of x starts at -2, -1, and then we use the x-axis. We start at -2, the next number going up on the x-axis would be -1, and then after -1, the next number on the x-axis is 0. So just think about the number line. Now these we plug into the function. So f of x was x plus 2 squared minus 1. So let's just double check that. I'm pretty sure that's what it was. X plus 2 squared minus 1, yeah. Sorry. Okay, so to finish our table, we plug this -1 in for x. So -1 plus 2 squared minus 1. -1 plus 2 is 1. 1 squared is 1, minus 1 is 0. And 0 plus 2 squared minus 1. 0 plus 2 is 2. 2 squared is 4. 4 minus 1 is 3. So there's my function, the table for my function. So -2, -1, -1, 0, and 0, 3. I'm not sure what happened here, but let's just do this so that's not confusing. Okay, and then if we do the inverse, we have, we just switch the columns. So we have -1, 0, 3 in the x column, -2, -1, 0 in the f inverse column. So let's plot both of those functions. You've got -2, -1, -1, 0, and 0, 3. Just start there, and it's half of a parabola. And then that's f of x. F inverse, we go to -1, -2, 0, -1, and 3, 0. Okay, so that's f inverse. And this was f of x. And then we also need our line of symmetry, x equals y. So 0, 0, 1, 1, 2, 2. This is the function y equals x, remember. That's what this table goes for. That's the line of reflection. So we have 0, 0, 1, 1, 2, 2, and if we keep going forever, it's just going to be all those numbers that are the same x and y. So y equals x. And now you've finished the problem. So today you have notes on logs, or yeah, it should say logarithms on the top in a big log. And logarithms are just inverse exponential functions. So one application of logarithms is to find the magnitude of an earthquake, because when an earthquake hits, it makes the vibration of the earth increase exponentially. And these turn out to be really, really, really big numbers. And so scientists made up a measurement scale using logarithms to make it more of a scale that would be more understandable and more user-friendly. We call that the Richter scale. So you might remember that there were several earthquakes in Mexico back in about a month ago. The first one was an 8.1 on the Richter scale, and that hit on September 7th off the southern coast of Mexico. And then about a week later, 12 days later, sorry, 7.1 magnitude earthquake hit again in about the same place. And then they had several smaller quakes after that. And we're going to look at what these numbers actually mean after we understand what logarithms are. So logarithms is just a special way to ask a specific question, and a logarithm looks like this. Log base b of n equals p. So we say log base b of n is p, where n, well, I'll write that down in just a minute what each of these are. But the question we want to answer, because it's just a special way to ask a specific question, is what exponent, I'm going to use power, sorry, what power is needed to go from base of b to equal a number n? That's the question we want to answer. And so basically, I'm going to show you what I mean by that question in just a minute, but we're going to answer that question. I'll refer back to what that means as we go through these. We have two forms. The normal form you're used to seeing is the exponential form, b to the p some base to a power equals a number n, like 2 to the second power equals 4. And now log base b of some number n is equal to that power. So if the base is b and we need it to equal this number n, what does that power have to be? That's what a logarithm means. So we're going to start, first of all, what does b equal? It means base, and p stands for a power, and n stands for some number. And so, for instance, if I have 4 to some power, what would that power have to be in order for the number to be 64? So 4 to what power equals 64? That's the question we want to answer. And that power would have to be 3, because 4 times 4 times 4 equals 64. So we say, if we go back to our formula, that means log to the base 4 of 64 is equal to that power 3. So log, let's do it in a different color, log base 4 of 64 equals 3. So the 4 is, we call it a subscript. It's a smaller number, kind of like the power is a superscript. And then the 64 is normal size and the 3 is normal size. So this would be the logarithm that is the inverse of that exponential. Another way to think about it is just to figure out what numbers are your b, p, and n. So if I had 5 to the third power equals 125, so I already know the power is 3. How could I write this as a logarithm? This is exponential form, this is log form. How can I write this as a log? Well, you know the b, the base, is 5, you know the power is 3, and the number n is 125. So you just put those in the spot they belong. The b goes here, the p goes here, the n goes here. So it would be log base b of the number n equals our power p, 3. And that's it. You wrote the log out. So you try, I have 2 for you to try. 7 squared equals 49. Write that in log form. And 10 to the third equals 1,000. Stop the video. Try those 2 and then come back on. Okay, so in this one we know b is 7, p is 2, and n is 49. So you would write log base 7 of 49 equals 2. And the last one, b is 10, p is 3, and n is 1,000. So you would write log base 10, and if it's base 10, you don't write the base, you don't have to. And normally if you see a log written that is base 10, they will not have written the base in. That's because 10 is the standard base of logarithms. So you could just write log of 1,000 equals 3. Now, if you wrote a 10 in there, I would mark it incorrect, but you would have to see, if you were doing a multiple choice test, you would have to recognize that if there's no base written in, that it's a base 10. So, base 10, no subscript. Okay, so what if I have a function that is already in log form and I need to switch it to exponential form expression? So let's say I have log base 3 of 81 equals 4. Well, you just go backwards. Figure out what b, p, and n are. So b is your base, 3. P is the power, which is this number on this side in a logarithm, because that's the answer to a logarithm, is the power. And n is the number that you're trying to raise your base to, so 81. So if I am writing this in exponential form, I would write b to the power equals the number 81. Okay, second example. Log base 2 of 8 equals 3. Well, b is 2, p is 3, and n is 8. So I would write b to the p, so 2 to the third power equals 8. That's what I would write. Okay, two examples for you to try. 5 to the third power equals 125. We already did that one on the other side, so that should be easy. And 10 to the fourth power equals 10,000. Stop the video and try those two. Coming back, you should have log base 5 of 125 equals 3, and log of 10,000 equals 4. So, now that we know how to convert logarithms, we're ready to take another look at the earthquake problem. So now we can calculate the intensity. How much more did the earth shake during those earthquakes than it's normally shaking? Because we know that from taking science classes that the earth is vibrating always. But when there's an earthquake, that vibration increases exponentially. So the first quake, and I have these backwards, the first quake had a magnitude of 8.1, and the second, the magnitude was 7.1. What was the intensity of each earthquake, and how much more intense was the first quake? Okay, so the equation for magnitude, this is magnitude, that's these numbers, the Richter scale. Intensity is the amount of vibration. Okay, intensity. How much more intense was the first earthquake? Well, looking at this, I have a logarithm, and it looks like it's base 10. So I know that I could switch this to exponential form if I plug in m. So for the first quake, m equals 8.1. So if I plug that in, and I'm going to put the 10 in just to make it easier to see what to do here, I could get the I by itself by just switching this to exponential form. So I could write 10 to the 8.1 equals the intensity. And if you put that in your calculator, 10 to the 8.1 10 to the power of 8.1. Let's clear that. I didn't look at that. We want to go to the main screen. Now we can do it. 10 to the power of 8.1, and it equals 125,892,541. So I equals 125,892,541. So that's how intense that earthquake was. Now let's compare to the second earthquake. So the second earthquake was 7.1. So if I put 7.1 equals log base 10 of I know that 10 to the power of 7.1 will give me that intensity. So put that in your calculator. 10 to the power of 7.1. And we get a similar number, almost the same numbers. Wonder why it did that. 12,589,254. So the intensity of the second one was less than the first one, but by how much? Well, I'm looking. These are both powers of 10. This one is just one integer higher power of 10. So in other words, we multiplied 10 by itself one more time. So this actually should be 10 times as much as this. So if I take and I divide these, take that number divided by that number, you just use your cursor to highlight those numbers, and then you can press enter. Well, our theory was right because it's 10 times more. So this one was 10 times as big as this, as intense as this one. So that's an interesting real-life application of these things, because every year when I teach this, kids are like, what is the point of this? And actually, logarithms are used in a lot of different fields. In the technology age, we don't do them by hand as often, but it's good to know what they mean so that in a career later in life, you might be using logarithms. At least you can understand what they mean and where they come from. And now to find the inverse of an exponential function, we need to use logarithms. So we're going to start with the same thing we always do. We have this function, f of x equals 2 times base raised to a power. So this we're going to call our coefficient for purposes of this lesson. This is our b to the p. So in other words, we have a times b to some power p. That's what we have here. So replace f of x with y and switch x and y. So this is y and then switch them. So I have x equals 2 times 3 to the 2y. And then before we convert, I want to make sure we isolate the b to the p. So in other words, if there's a power here, or I have some plus, some number, some constant here, we get rid of this number and we get rid of the coefficient. In this case, we just have a coefficient. So we're going to divide by that 2 on both sides. So now I have x over 2 equals 3 to the power of 2y. Now I can convert to log form. Convert to log form. Okay, so I've got x over 2 equals 3 to the 2y. So what is b? Well, b is this number 3. Now we're putting variables in here, but it still works the same way. My power is 2y, and n is the number on the other side, which in this case is an expression, x over 2. And then we want to get, once we get this in log form, we'll solve for y. So let's see, log base b, base 3, of some number n, x over 2, equals 2y. And now we want to solve for y. So what would we do? Well, we'd divide by 2 on both sides. So remember, when I divide by 2, that's the same as multiplying by 1/2. So I'm going to say 1/2 of the log base 3 of x over 2 equals y. There is one more step in here, but since we're not teaching you the log properties this year, I'm not going to do that step. I'm going to leave it like this for today. So we're just going to replace the y with f inverse of x, and we write f negative 1 of x equals 1/2 log base 3 x over 2. And that's where we're going to leave the answer for today. So there's 2 examples for you to try. If you just follow the steps we just wrote, don't forget when you have a 1/2, you can multiply by 2 on both sides to get rid of that half. So to do this problem, I'll let you stop the video, and I'm going to do the problems. Come back on when you're ready. So we've got f of x equals 1/2 times 2 to the 3x. Well, let's forget that. Okay, so this is like y equals 1/2 times 2 to the 3x. So this is my b to the p. I need to get rid of that 1/2. Well, first let's switch the x and y. Now I want to multiply both sides by 2. So multiply by 2, multiply by 2. What happens here is the 1/2 times 2 just equals 1. So that equals 1. And on this side I'll have 2x. So I have 2x, so 2 times x equals 2 to the power of 3y. Okay, so the next step was to convert to log form. So b is 2, so log base 2 of n, so power was 3y, and n is 2x, of 2x equals, I'm sorry, log base 2 of 2x, I was right, equals 3y, sorry. So now I just want to solve for y by dividing both sides by 3. So I have 1/3 log base 2 of 2x equals y. And again, you would break this up using the product property, but we're not going to do the properties yet. So we're just going to leave it like this, and I'm going to put my inverse function equals 1/2 log base 2 of 2x. Okay, and then the second example, we have y equals 2 times 4 to the power of x minus 1. So x equals 2 times 4 to the power of y minus 1. If I need to isolate my b to the p. So this is the b to the p. This is my coefficient. So I divide by 2. So I have x over 2 equals, that's 1. So 4 to the power of y minus 1. So b is 4, p is y minus 1, and n is x over 2. So to write it in log form, I write log base b, which is 4, of n, x over 2, equals p. Now, this is y minus 1. So we don't divide by 1 here. This opposite, the inverse of operation of subtract is add. So instead of dividing here, we're going to add 1 to both sides. So you just have to do the opposite operation. So now I have y on the right hand side, and I have 1, or the log base 4 of x over 2. Now this is all one thing. You don't break that up and add 1 to the we call this the argument. You just put plus 1 on the outside of the log. So you have f negative 1 of x equals log base 4 of x over 2 plus 1. And that's the final answer. Okay, so you have a worksheet with 8 problems on it. And I gave the solutions to your teacher. So if you need help, either stop with me or Mr. Easter, or go or look at the solutions that I gave your teacher.